Welcome to the Continuing Education Centre at ECAE, Emirates College of Advanced Education. And welcome to Foundations of Chemistry Day 1 training. I'm looking forward to you all joining in and having a positive time with us here at CEC. Please get comfortable, get ready for a lovely day's training. So here we are, Foundations of Chemistry for Cycle 3 educators. Let's have a look at what the training is going to take us through today. Ground rules, first of all. Of course, be respectful of one another. Even if you're watching this online or together in a team, make sure that we have good collaboration, we stay on target. I'll do my best to stay on time. And let's not answer our mobile phones whilst we're in the training. We do have a parking lot for you today, so if you have any questions that you'd like to ask whilst we're online, you can write them into the chat box and I'll be happy to address them as we go through or at the end of each section. So, the agenda for today. Obviously, we'll go through the aims and objectives in a moment, but the main topics that we hope to cover with you guys today are the scientific method, scientific notation and derived units, properties of matter, all the way through from the basics of elements, compounds, and mixtures right through to atomic number, mass number, and electronic structure. And then at the end of the day, we'll be looking at applying the Aufbau principle. So let's get started with the day. Our aim today is to review some of the Cycle 3 chemistry concepts that you find in the curriculum that you teach. By the end of the day, I'm hopeful that you'll all be confident in interpreting the scientific method, defining and providing examples of derived units, summarizing the classification of the matter of elements, compounds, and mixtures, categorizing chemical reactions and changes and physical changes, identifying the number and mass number of a range of Okay, so today's aim is to review Cycle 3 chemistry concepts that you find yourselves teaching in our schools. The objectives of the day are, well, we're hopeful that you will go away being able to interpret the scientific method, define and provide examples of derived units, summarize the classification of matter into elements, compounds, and mixtures, be able to categorize chemical and physical changes, be able to identify atomic number and mass number of a range of different elements, be able to assign the electronic configuration of an atom up to Z, and finally apply the Aufbau principle. If there's any questions about the objectives, please feel free to write a message in the chat box. Okay, so let's get started with our day. We're going to start with a really great starter, something that you guys could use in your classrooms. Feel free to note down the website. It is Bamboozled. It's a fantastic place to take your students and yourselves, which I'm going to do with you in just a moment. We've divided you into teams. If you're watching this online, please feel free to use the link and play in a team or individually. Let's go play the game. Okay, guys, so are you ready? This is our Bamboozle game. We've got two teams with us today. Team 1 are going to start. What number would you like to go with? Team 1, I hear you say 7. Let's see. You have 30 seconds to answer this question. What is collision theory? 25 seconds down. Oh, I can hear a few discussions going on. Okay, shall we check that answer? Oh, are you sure? Are you ready? 16 seconds left. 14. Let's. A theoretical model that accounts for the rates of chemical reactions in terms of collisions between particles occurring during a chemical reaction. I'm going to give you that one, but next time remember to make sure that you say collision between particles. Well done. Right, Q, are you ready? What number are you going for? I hear you saying 12. Let's go. What is the term of a chemical species that donates electrons in a redox reaction? I can hear you discussing. What are the answers? Where are we? 22 seconds down. Let me know when you're ready to answer. Remember, we're talking about redox reactions. You've got to be specific with your answer. Let me know when you're ready. 12 seconds down. Okay, let's check. Well done. A reductant. Excellent. That's 15 points for you guys. So we're neck and neck. Right, team one, you're going to go for number 13. In a Daniell cell, at which electrode does oxidation occur? Time's ticking. Let's see where you are. Time's ticking down. A Daniell cell. Have you reviewed this in your curriculum yet? Let's have a look. Oh, are you sure you want to answer? Let's have a look. An anode. Well done. Excellent answer. Good discussion there. Okay, team two, what number are you going for? 15. Excellent. This is something we often get students to do, and it's something that we've learnt about a lot as chemistry teachers. State Le Chatelier's principle. Can you tell me exactly what the principle is? Oh, you're going for it very early on, 19 seconds. Are you sure you don't want to check your answers? Okay, you sure? Let's go. Le Chatelier's principle. If a system at equilibrium is subjected to a change, the system will adjust to partially oppose the effect of the change. Excellent definition. I'm going to give it you because you did mention system and you did mention adjusting and changing. Excellent. Well done. And remember, equilibrium. Okay. So team two are on 35 points. Team one, number 5, let's go. Oh, another question on a Daniell cell. In a Daniell cell, at which electrode does reduction occur? Oh, you're hitting me early with this answer. Let's go then check. Fantastic. Cathode. Everybody's on form today. You're all getting your answers right. Come on then, team two. Where are we? Where do you want to go? Number 10. Wow, look at that. 10 points for free. Excellent choice. Right, we're neck and neck now. Team one, number 16. Oh my goodness, what's going on here? You've just won 25 points. Okay, team two, number 9. What is the general equation for Kc? Do you guys remember what Kc is? Are you conferring? See if you can work it out between you. Let me know when you're ready. Come on, 17 seconds down. Are you sure? 9 seconds. 8. Okay, let's check. Products over reactants. Well done. Fantastic. Nobody's got any answers wrong today. We're doing really well. Okay, number 4, I hear you say, team 1. Swap points. So sorry. Team 2, you're now in the lead. Okay, team 2, number 14. What is an electrode? This should be an easy one for you all. Oh, and it is. You're coming in with an answer early on. A solid conductor in a half cell at which oxidation or reduction reactions occur. Now, I'm sorry, Team 2, I'm not going to be able to give you that one because whilst you got solid conductor, you did not mention oxidation or reduction. and we needed the specific language there. Okay, there's 5 points in it at the moment. So team 1, you want to go for number 1? Okay, let's go. What type of intermolecular force exists between molecules where a H atom is covalently bonded to O? Our absolute favorite chemistry teachers, intermolecular forces. 17 seconds left. 15. Are you ready with an answer? Let's go. 12 seconds. Fantastic. It was an easy one. Hydrogen bonding. Fantastic. Okay, team 2, let's see if you can pick up some of these points. Number 11, you say. What is the term for a substance that conducts electrical energy as a result of dissociating negative and positive ions? I hear you coming in with an answer very quickly. You sure you don't want to check that? Still got some time left. Okay, let's go for it. An electrolyte. Well done, fantastic. Okay, team 1, number 8, here you go. What is fracking? F-R-A-C-K-I-N-G, fracking. I can hear you discussing in the background. What do you think the answer is? Those of you watching online, don't use Google. Let's see if we can remember our chemistry. Oh, team 1 are in with an answer. Let's see. The process of interjecting sand, water, or chemicals at high pressure into coal or rock to release natural trapped gas. Now, I'm afraid, team 1, I can't give you that because although you talked about injecting sand, water, or chemicals at high pressure into coal or rock, you didn't give us the reason, the product, which was the release of the naturally trapped gas. Good effort, though. Okay, now there's 10 points in it. Team 2's in the lead. Let's have a look. Number 6, you say. What is the term of a chemical species that accepts electrons in a redox reaction? Think about it carefully. Time's going. Accepts electrons. Oh, you think you've got an answer? You want me to check it? Are you sure? Okay, let's go. Well done. It is an oxidant. Right, team 1. Let's see what you can do. Number 2. What is the activation energy of a reaction? Are you sure you want to give that answer? You've still got some time to think. You're coming in very early. Let's check. Exactly. Activation energy is the minimum energy required by reactants for a reaction to occur in order to break the bonds between reactant atoms. Fantastic. Well done. Only one question left. Let's see. What type of reaction results in a positive enthalpy value? Definitely cycle 3. Chemistry. How are we doing here? Time's going, team 2. This is the final question. Are you sure you want to give that answer? Okay, let's go. I'm afraid, right on the last question, you answered exothermic and the answer was endothermic. So it looks like team 1 won. Well done. Excellent game. Fantastic starter to the day. And we've done some fabulous chemistry revision to start off with. Well done, guys. Okay, so let's look at our first topic of the day, scientific method. This is something that we all teach from cycle 1 all the way through to cycle 2 and 3, even at degree level. We never stop using and looking at the scientific method. You might have a PhD, you'll still be using it. You might be a teacher in a classroom. You might be a mother at home and not know you're using the scientific method. And that's what we're here to think about and look at what the actual scientific method means in everyday life and how we use it in our classrooms and how we can get a better understanding of it for our students as well. So we've got a small activity to conduct now, and it's a discussion. I'd like you, if you're watching online, find someone to discuss this with, or personally note down some ideas, and then start thinking about how science is a systematic and logical approach to discovering how things in the universe work. It's a body of knowledge, we know that. This is how we make discoveries about things in our entire universe. And it's something that scientists continually use to challenge our current beliefs, to think about progress, to build on ideas that have come before, asking questions, experimenting to gain new knowledge. And then we have to ask ourselves the question, as scientists, as chemistry teachers, why is the scientific method needed? So let's have a look at the activity. Firstly, what I'd like you to do is to think about the scientific method and how it's used in everyday life to solve problems. Can you remember what the components are? Take a few minutes, note them down. Don't try to Google, see what you can remember. And then once you've done that, I'd like you to discuss with a partner, if you're not able to meet up with someone, again, do some brainstorming. Can you think of how you've used the scientific method? Not just in your classroom, not just in teaching chemistry, but in everyday life. So I'm going to give you about 10 minutes to do that activity. Really do some scientific method soul searching, and I'll be back with you in 10 minutes and we'll have a great discussion. Okay, so welcome back. Some fantastic discussion there. So, in your discussions, you brought up what we see here in front of us. A list of areas that I'm not going to define for you yet, the order, that are involved in the scientific method. And what is the scientific method? It's the process used by scientists to understand the natural world. It's fantastic because it allows us to investigate natural phenomena in a very rigorous manner. We can work from hypotheses to draw conclusions based on empirical data. So that concept is very important, empirical data, drawing conclusions. When we get to a point that we're able to validate large-scale numbers of data, we can actually start to look at intrinsic variability in the world around us. So science in itself invites a lot of criticism, or especially at cycle 3 when you're talking to non-scientists, that possibly the everyday person doesn't understand. But if we think about the scientific method as logical reasoning, we can then start to adapt that to how we apply it in our classrooms, how we get our students to have an understanding of it and apply it in the laboratory. So this idea of scientific method being basically logical reasoning is something very good for you to base your ideas and discussions on about the scientific method. Let's not forget about the concept of cognitive bias, which makes us all possibly at times overestimate the relevance of or underestimate the relevance of our behaviors and choices in inferring or hypothesizing or coming up with ideas. Our cognitive bias affects our ability to think rationally, but scientific method takes cognitive bias out of the equation. And that's why I like to think about it as logical reasoning. So Scientific method has its roots in the 16th and 17th centuries. Philosophers Francis Bacon and René Descartes are often credited with formalizing the scientific method, and that's simply because they contrasted the idea that research should be guided by metaphysical preconceived concepts of the nature of reality. So if we then take that idea to what I was saying to you in terms of logical reasoning, that's where we are at cycle 3, and that's what we want to be able to demonstrate an understanding of, so that we are able to teach our students the universally accepted scientific method, which is, as we all know, firmly grounded in, as I said earlier, hypotheses, gathering data, and drawing conclusions. So now I'm going to give you a chance to watch a short video, which you can easily find on YouTube, but it's an excellent one just to revise the concepts and refamiliarize ourselves, as one might say. But at the same time, it will give you something that you might be able to use in your classrooms as well. It's a really good discussion with you all, and I hope that this small section on scientific method has got you thinking again about something that we often just put to one side when we're teaching science and chemistry. So let's take a look at the video now.
The scientific method is about ordinary people doing ordinary things. That includes you, me, and other scientists in the world. The scientific method is just a process or steps taken to produce reliable results to answer a specific question. Maybe you think you don't use a scientific method in your life, but I can guarantee that you do. For example, imagine you wake up on a Saturday and you couldn't find your cell phone. That's an observation. Then you do a little research by thinking about the last time you had it. You suspect that it might be in the pocket of your pants from yesterday. That's a hypothesis. And when you check your pants, you're doing an experiment. But science and life don't always go as planned, and you find no cell phone in your pants pocket. So the second observation leads you to think again and recall what else you did yesterday. You remember that you put your cell phone in your backpack during school. So you decide it must be there, and you go and check. And lo, there it is. Life can continue, and you're so happy that you share the results with your best friend and explain why it took you so long to text them back. Science. These are the steps of the scientific method, and at any step, you can go back and repeat the process. Typically, after you conduct an experiment and conclude that your results aren't answering the question, you go back and try something else. And really, truly, observations and research are going on the entire time. Science is a continually ongoing process. Now let's break down each of these steps into their component parts. All that can be observed with the 5 senses are included in observations. You use your sense of smell, sight, taste, touch, and hearing to make your observations in science. Research is an important step in science because it may answer other questions you have and help refine your experiment before you go down a path that leads to nowhere or conduct an experiment that's already been done. Make sure you use reliable sources to learn background information. Scientific journals and online sources that are vetted and trusted are best. Avoid information from blogs and out-of-date textbooks, as the information might not be reliable. Once you have your research completed, you can form your hypothesis, which is a prediction of what you believe will occur. It is often seen as an if-then statement and is very specific. Here's an example. If gummy bears are placed in water for 24 hours, then they will swell to over twice their original size. It has an if and a then, and uses specific terms that make this experiment repeatable. The experiment itself is made of several parts. Most experiments collect 2 types of data, qualitative and quantitative. Qualitative data relies on descriptions like soft, yellow, shiny, or wet. Quantitative data relies on numbers like 25 centimeters or 2.3 grams. Once you know what types of data you're going to collect, you can define the variables in your experiment. There is the independent variable, which is the thing you change to see how it affects your dependent variable, which is the thing you measure. So in the gummy bear example, the change in the experiment is that the gummy bears are being placed in water. The dependent variable is the volume of the gummy bear, which is measured before and after it's soaked in the water. A valid experiment will have both an experimental group, where the independent variable is altered, and a control group, which can be used to compare the experimental group to the normal or unaltered version. In the gummy bear experiment, the bears placed in water are the experimental group, and the dry gummy bears are the control, because that's how gummy bears normally are. So to summarize, an experiment should have an experimental group and a control group. The experimental group will have an independent variable and a dependent variable, and the data that is measured and collected can be qualitative, quantitative, or both. Thanks for watching this episode of Teacher's Pet. Don't forget to like and subscribe, and follow me on Twitter at SciencePet.
Okay, guys, so that's a great reminder in that video, and it's something that you can easily find on YouTube to use in your classrooms and also to revise things for yourself. So there we're done now with scientific method. Let's see how you got on with your understanding. A quick question, very short quiz. Let's see what you all think. What is a rational explanation of a set of observations called? A proposal. B, a postulate. C, a prediction. Or D, a theory. What do you think? Let's have a look. Choose your answer carefully. It is a theory, a rational explanation. Remember, we were talking about hypothesizing and gathering empirical data. So it's a rational explanation when we think of a set of observations, put them together, and we get a theory. Okay, next. Which of the following is the correct order of steps to establish a theory? A, conducting experimental work, collecting observations, making a hypothesis, establishing a theory. I'm hoping whilst you're reading these, you're thinking back to the video that we just watched. B, establishing a theory, conducting experimental work, collecting observations, making a hypothesis. C, collecting observations, making hypotheses, conducting experimental work, establishing a theory. D, making a hypothesis, collecting observations, establishing a theory, conducting experimental work. Let's see how you did with that one. The answer is C, just as we watched in the video and just as we discussed whilst we were looking at the scientific method. So that's something to imprint on our minds. Collecting observations, making a hypothesis, conducting experimental work, and then establishing a theory. That's what we're thinking about when we are looking at the scientific method. So now we've reviewed that and you've had your discussions, you've thought about how it impacts your everyday life, how you can use it in the classroom. I hope it's a good reminder and a good review of the scientific method, and I hope you take it back to the classroom and back to your own work. So we'll move swiftly on now to our second topic of the day. Derived units, every chemistry teacher's favourite. So why do we have to look at this in Cycle 3 chemistry? Simply because we have SI units and we have derived units, and we need to ensure that we have a good understanding of them so that when we are doing our calculations in all different areas of chemistry, we are equipped to make and annotate with the right units. Okay, so these are some of the SI units that we use in the classroom. In cycle 3, mass is measured in kilograms, length in meters, amount of substance in moles, temperature in Kelvin, time in seconds, force in newtons, and energy in the good old joule. So, derived units. Let's have a think about the visual side of things. So, the more commonly used metric unit, the litre, is derived by cubing the decimeter. So a decimeter, as you can see from the diagram, is 1/10 of a meter and is therefore also referred to as the cubic decimeter. So 1 litre is equal to 1 cubic decimeter. Right, so let's have a look at some other very frequently derived units that are used in chemistry. And don't forget, by derived, we mean calculated. So, speed, distance over time, can anyone remember what speed is measured in? If we have speed, which equals distance over time, so that is meters over seconds. Density. Mass divided by volume. Mass is measured in kilograms. Acceleration. Distance divided by time squared. Meters divided by seconds squared. Force. Yep, you got it right. Mass times acceleration gives us the Newton. Pressure, force over area, pascals. Energy, force multiplied by the distance, giving us the joule. So you might want to take a moment to take a screenshot or note down these derived units because we will be using them later. And re-familiarize yourself with them as chemistry cycle 3 teachers. It's always good to be able to explain the derived units to our students, but also practice doing calculations with them. So let's move on to the next area in derived units. What are we talking about? We're talking about scientific notation. So what exactly do we mean by scientific notation? Scientific notation, well, let's start with regular notation, the standard way that we write our numbers. For example, 208 million is written as you see it on the screen. Scientific notation can be thought of as a shorthand way of writing very large or very small numbers. So how we describe it is that a number is written as the product of two factors. And you can see all of your examples there. And again, I really want you to take note of these now. Refamiliarize yourself, because the next activity we're going to do, I'm going to ask you to work in pairs or individually as a group, as you see fit. It's better to do a think, pair, share at this point, I would say. And we're going to actually try to do some calculations with derived units. Very similar to what a Cycle 3 teacher would use in the classroom and typical of the level of knowledge that would be required for a Cycle 3 teacher. Are you ready? Let's have a look at the task ahead. So, I hope you took your screenshot. If not, you can rewind after you've had a look at the questions if you're watching the video. Now, what we need you to do for this task is calculate using the derived unit. So let's have a look at question 1. The volume of a rectangular solid is 150 centimeters cubed. If it has a mass of 300 grams, what is its density? Second question. A dog runs from one side of the park to the other. The park is 0.08 kilometers across. The dog takes 16 seconds to cross the park. What is the speed of the dog? Third question. You give a shopping cart a shove down the aisle. You push it down the aisle. The cart is full of groceries and has a mass of 1,800 grams. The cart accelerates at a rate of 3 meters per second. How much force did you exert on the cart? So those are your 3 questions. Don't forget to put your working out. Remember that you're thinking about the derived units. Read the questions carefully, and we'll come back in about 20 minutes with your answers, and we'll discuss how you calculated and what you got to. So I'll meet you back in about 15 minutes. Okay, guys, welcome back. I'm sure you enjoyed doing some calculations there. Don't worry, we've got a quick break coming up soon. So let's have a look at these questions and see how you did with your calculations and the answers. So first question was, the volume of a rectangular solid is 150 centimeters cubed. Cubic centimeters. If it has a mass of 300 grams, what is its density? Let's have a look at the answer. So density, the calculation, is mass divided by volume, which means that the density is 2 grams per cubic centimeter. Next, a dog runs from one side of the park to the other. The park is 0.08 kilometers across. The dog takes 16 seconds to cross the park. What is the speed of the dog? Something in here that maybe some of you missed, but let's have a look. So, speed, nice and simple, distance divided by time. However, remember when we're looking at our derived units, we must use the correct unit. So we need to change that 0.08 kilometers, you got that right, into meters. The time given in the question is correct. 16 seconds, no need to convert that. Therefore, the speed is 5 meters per second. Quite a speedy little dog there. Okay, last question. You give a shopping cart a shove down the aisle. The cart is full of groceries and has a mass of 1,800 grams. The cart accelerates at a rate of 3 meters per second squared. How much force did you exert? A little bit of a complicated one there. Let's see how you all did. So we know that force is equal to, yep, you got it, mass times acceleration. So the mass is 18 kilograms. Convert those grams to kilograms. Don't forget to do that. And you are given the acceleration, 3 meters per second squared. So then it's a nice and simple calculation. 54 kilograms per meter squared. That's the force you exerted. Well done with those calculations, and don't forget to go online, find some more examples, even look through your student books and actually sit down and do the calculations yourselves to revise, to feel more confident in doing these calculations and review your knowledge of the derived units that we teach all the way through cycle 3. Okay, guys, so time for a quick coffee break. We'll meet back in about 10 to 15 minutes. If you're online, you can go straight forward to the next part of the session. And the rest of you guys will meet back up in 15. Welcome back, everyone. I hope you had a lovely quick break. Stretch those legs, get those brain cells moving. Now, let's move on to the next part of the day. And what we're looking at now is classification of matter. So this is something, again, that is taught all the way through from cycle 1 right through to cycle 3. You will find a very nice pack of information in the resources that go with this training. It's all about the classification of matter, particularly related to the cycle 3 and what's expected of cycle 3 teachers over here in the UAE. So let's have a look and remind ourselves about some of the points that we need to refer to as cycle 3 chemistry teachers. Now, the first thing that I'll do is get you to have a little think. So when you think about chemistry, we've talked about this previously, what does chemistry mean to you, and why do we teach chemistry? Why do we study it? I'd like to hear from you guys what you mean in the chat box, what chemistry means to you. So let's have some answers, please. Okay, so chemistry is the study of matter and energy and the interactions between them. We have inorganic and organic chemistry. It's a physical science. Very good. Excellent. Chemists can go into many different fields. You can be a chemistry lawyer. You can study chemical engineering. You can make fireworks if you want to. There's so many fields that you can go into with chemistry. And again, we go back to that idea of the idea that we looked at earlier of the scientific method, where chemists pose questions and test hypotheses with experiments. These days, you don't need to physically be in a laboratory. You can actually develop theories using computer simulations. There's just so many things that chemists can go into in terms of a career profile. So, you know, chemistry is all around us. It's in photosynthesis, which is usually thought of as biology, but the chemical reactions that happen there, the chemical reactions that happen in all living beings, all animals, human beings, plants, as well as the things that we demonstrate to our Cycle 3 students in the laboratory. We have organic chemists, inorganic chemists, analytical chemists, physical chemists. There's many areas of chemistry that we don't actually think about as Cycle 3 teachers when we're teaching the curriculum. So we do need to have in mind when we're thinking about chemistry and what it means to us. whilst we move on to this recap on matter. What is matter? So I know pretty much, if I ask for some hands up, you'll all be able to tell me about the classification of matter. So yeah, matter can exist in different forms. And if we start by thinking of the questions that we would ask, and I'll ask you to think about critical thinking here and what you get the students to do in your classroom and how you should actually be thinking about yourselves. Very often we give students questions, but it might be pertinent to think about asking students to come up with questions before we ask them to answer them. So if we look at the diagram here, very simple, something that you've all will have come across a lot in your chemistry teaching. 3 simple questions. Can it be physically separated? Is the composition uniform? And can it be chemically decomposed? And there, from the questions, we get some very specific answers where we start to think about homogeneous mixtures, heterogeneous mixtures, compounds, and elements. And that is essentially where we take our students at Cycle 3 when we're thinking about the classification of matter. Traditionally, of course, when we think about matter and we recap the learning, we think about a mixture, something composed of 2 or more forms of matter that can be separated physically. A compound, you need to have, there is no physical separation and they're chemically bonded together. An element, something made from entirely one atom. Heterogeneous mixtures, different substances that remain physically separate. Homogeneous substances, uniform composition and properties. And subatomic matter, which is very important at Cycle 3 chemistry level, where we start looking at protons, neutrons, and of course electrons. So that's a quick recap. And if we then go through to the key points that we need to know at Cycle 3, we're now looking at the fact that we know matter exists as solid, liquid, or gas. Of course, there are other possible states, which we'll discuss later. We know that solid particles are tightly packed. They retain their shape and they're not free to move around. We know that liquid matter is more loosely packed, takes the shape of its container. They can move about within a liquid, but they're packed densely enough that their volume is maintained. We then have gaseous matter, where the particles are so loosely attached that there has neither a defined shape nor defined volume. And gases, of course, can be compressed. So we're going to do a quick activity, and I will refer you to the resource pack where you have a whole booklet all about the different states of matter and the properties of matter, more essentially. You can find the booklet in the resource pack, and its title is The Properties of Matter. And what I would like you to do is go through the document and think about how you would take the key information from this document. And I'll show you some of the pages in a moment on a screen share now about how you take the key information from this document and design either an infographic, a short video, something that is informative to students that you'd be able to both use as a recap for yourselves and in your teaching. So, oops, let's go back. Okay, so let's have a look at the activity. Now, it might seem like something simple to yourselves right now, but as I said, I'd like you to use the resource pack that is available, and I'll do a screen share with you, to create a resource that you would be able to use with your students and also as a recap with each other for defining the properties of matter. So you can see I'm sharing the resource online with you here. If you're doing this course at a later date, you'll be able to find it in the resource pack. And the areas that we look at in this booklet are, of course, defining matter and states of matter, changes in matter, the classification of matter and separation of mixtures. Lots of lovely objectives listed and linked to our course today. Now, what I would like you to do over the next 15 minutes is start to plan the development of an infographic, a YouTube video, anything that you think is appropriate to be used in the classroom as something where you can start to use a resource to teach your students about the cycle 3 chemistry of matter and the properties of matter. And I'm just quickly flipping through the booklet here so that you can see there's plenty of information for you to use. If you're working in a group, I would suggest that, different groups use different areas of the booklet. It's entirely up to you. The point of this Foundations of Chemistry course is a recap to have a look at the chemistry that we've learned along the years of being chemistry teachers and recap in what we teach the students and the information that we need ourselves. So you'll see it's a lovely booklet with a lot of information for you here. But what I would like you to do is create a summary of the information and then present it to each other so that we're both reviewing the information ourselves and then we are experimenting with different ways of presenting the information. You've got about 15 minutes to start that task, and then later on in the day you can take some time and then complete it so that you actually go away with a resource that you can use in your classrooms. And you'll see that this booklet is quite extensive. It goes over a lot of different areas specifically related to matter in cycle 3 chemistry. So I'm looking forward to you sending those through. And that's 15 minutes. If you're live with me, I'm here in the chat box if you need to know anything. If you're following the course at a later date and it's recorded, please refer to the resource pack where you will find this lovely document called The Properties and Structure of Matter. Okay, so I hope those of you that are following online did some Googling and had a look at the resource booklet, and those of you that you are participating, thank you for sharing some fantastic infographics and video ideas. Always try to come up with new ideas and ways that you can create resources that you can continually use in your classrooms. So we go through the main properties of matter that we need our students to be able to know of at cycle 3 level, and just take a moment to review these. Okay, well done. So let's move on to the next part. A quick quiz. So diagram A shows a compound made of 2 elements. We've got green and red spheres and they are in the liquid state. Can you tell me in diagrams B to D which of them represent a physical change and which of them represents a chemical change? So in A we have liquid state, B, C and D. What do we have represented? Where have we got a chemical change? Let's have a look. Yep, you guessed it. You can clearly see that the atoms are now bonded differently. In B, we now have the red spheres with the red and the green with the green, a chemical change. In C, they are completely separated. There's no bonding between those elements anymore. So both B and C represent a chemical change. And then D, that is a physical change, because if you look at diagram A, the compound is tightly packed. It's not taking up a large volume, it's quite compressed, and when you move to D, each of those molecules made up of the green and red spheres are now quite loosely arranged and not as quite tightly packed, so it represents a physical change. Well done, guys. Okay, so let's move on to the next item on our agenda, atoms and elements, another good area of revision to do. For the atoms and elements section, again, in the resource pack, you will find some Royal Society of Chemistry information packs and activities that you'll be conducting in this part of the training, which of course you can then also go on to use in your classrooms. So let's skip to it, atoms and elements. So, atomic size, something that's always quite difficult for students to conceptualize. And we quite often use diagrams such as those that you've seen represented on the screen there. The development of the modern atomic theory revealed a lot about the inner structure of atoms. We've learned that atoms contain a very small nucleus composed of positively charged protons, uncharged neutrons, surrounded by a much larger volume of space containing negatively charged electrons. Yep. The nucleus contains the majority of an atom's mass because protons and neutrons are much heavier than electrons, whereas electrons occupy almost all of an atom's volume. The diameter of an atom is on the order of 10 to the 10 m, whereas the diameter of the nucleus is roughly 10 to the 15 m, about 100,000 times smaller. So that's why we have this diagram for a perspective about their relative sizes. If the nucleus were the size of the blueberry, the atom would be about the size of the football stadium. It's a good analogy to represent to our students. So we all know elements, periodic table, something that our students and ourselves we have much fun with. So the ancient Greeks theorized that everything was made of fire, earth, water, and air, and of course we know very differently. And it was in 1805 that John Dalton, very famous, we've all heard of him, started to refine a vague idea that matter was indivisible. And this is where his theories have taken us into modern day science. So Dalton predicted that each element was made of a type of atom, and he started to create symbols for them, as you can see there on the screen. He also theorized about compounds. So Dalton's theory proposed that all matter was composed of atoms, indivisible and indestructible building blocks, while all atoms of an element were identical, and different elements had different atoms of differing size and mass. Dalton's atomic theory also stated that all compounds were composed, as you can see in the diagram with the different colour spheres, of combinations of those atoms that were elements in different ratios. And then he also postulated that chemical reactions resulted in the rearrangement of the reacting atoms, as you can see in the bottom layer of those diagrams. So we can say that the concept of the atom dates back, right back to Democritus, an English meteorologist. John Dalton then took that information and formulated the first modern description of an atom being the fundamental building block of all chemical structures. He went on to develop the law of multiple proportions, which was first presented in 1803, and he did this by studying and expanding the works of Antoine Lavoisier and Joseph Proust. Dalton believed that atomic theory could explain why water absorbed different gases in different proportions. For example, he found that water absorbed carbon dioxide much better than it absorbed nitrogen. And he hypothesized that this was due to the differences in the mass and complexity of the gases' respective particles. And we do now know that carbon dioxide molecules are much heavier and much larger than nitrogen molecules. Dalton proposed that each chemical element is composed of atoms of a single unique type, and though they can't be altered or destroyed by chemical means, they can combine to form more complex structures, which we now know as chemical compounds. So if we go back to the beginning of the day and we were, looking at our revision of the scientific method, that's how John Dalton reached his conclusions: experimentation, examination in an empirical manner. And that's what really marked this first true scientific theory of the atom. So let's just recap. Dalton said everything is composed of atoms. They are indivisible building blocks of matter. All atoms of an element are identical. All atoms of different elements vary in size and mass. Compounds are produced through different whole number combinations of atoms, and a chemical reaction results in the rearrangement of atoms in the reactant and produce product compounds. Now, obviously, atomic theory has been revised since John Dalton's first theories, and we now incorporate the existence of atomic isotopes and interconversion of mass and energy, and then the further discovery of subatomic particles has shown that atoms can be divided into smaller parts. But we can't forget the importance of John Dalton's theorization and experimentation leading to this modern atomic theory. And that's recognized by the designation of the atomic mass unit as a Dalton. So Dalton's ideas about the atom take us now nicely on to the next area of theory, Rutherford's gold foil experiment. So in 1909, Rutherford, along with some other quite famous scientists, started to look at something that we now know as the gold foil experiment. It's quite famous. His co-workers that I mentioned were Hans Geiger and Ernest Marsden. And what they did was they initiated a series of groundbreaking experiments that actually completely changed our ideas about an atom or the model of the atom. The experiment that they did was very simple, and I'm sure you all know about it. They basically bombarded very thin sheets of gold foil with fast-moving alpha particles. Alpha particles, as we all know, are a type of naturally radioactive particle, and they're positively charged with a mass about 4 times that of a hydrogen atom. Now, according to the previously accepted atomic model, where an atom's mass and charge were uniformly distributed throughout the atom, the scientists at the time doing the experiment hypothesized and expected that all of the alpha particles would pass through the gold foil with only a slight deflection or none at all. Now, do any of you know what actually happened? How well do you know Rutherford's experiments? So surprisingly, while most of the alpha particles were undeflected and did, as you see in the diagram there, pass straight through, a very, very small percentage, bounced straight back. No prior knowledge from Dalton's work or previous scientists had prepared Rutherford and his colleagues for this discovery. In fact, in a famous quote, Rutherford explained that it was if you had fired a 15-inch artillery shell at a piece of tissue paper and it came back and hit you. So Rutherford needed to conduct further experimentation and come up with an entirely new model of the atom. And because the vast majority, most of the alpha particles had passed through the gold, his reasoning was that most of the atom was empty space. In contrast, the particles that were highly deflected must have experienced a powerful force within the atom. Therefore, Rutherford concluded that all of the positive charge and the majority of the mass of the atom must be concentrated in a very small space in the atom's interior. Can you guess what that was? Yes, the nucleus. The nucleus is the tiny, dense, as we've discussed, central core of the atom, and it's composed of protons and neutrons. So Rutherford's atomic model then became known as the nuclear model. And in the nuclear atom, the protons and neutrons, which comprise nearly all of the mass of an atom, as we discussed previously, are located in the nucleus at the center of the atom. The electrons are distributed around the nucleus and occupy most of the volume. So Rutherford's discoveries and model proved to be a very, very important step, as you all know, towards understanding that of the atom. But it didn't address everything that we now know about the nature of electrons and the manner in which they occupy a vast amount of space around the nucleus. And it wasn't until some years later that we started to develop a good understanding of the electron. I'm going to show you a short video now about Rutherford's experiment, the gold experiment. And then we're going to actually move on to electrons, electron shells, and start to look at how we teach this in cycle 3. The video you'll watch should be a good synopsis of Rutherford's experiment and serve as a good reminder for all of you. But what we're doing here is we're going through the discoveries of the atom, and you will find in your resource pack a excellent resource, which I'll show you after the video, that you can use yourselves throughout this course whilst you're studying today, to remind yourselves about the discovery of the atom and the timelines, and you can use it in your classrooms. It's from the Royal Society of Chemistry, who are fantastic at giving us resources, both to review our own knowledge as chemistry teachers and to use in our classrooms. Do feel free to go and look at their website and join them. It's free, and you'll get a lot of annual resources. So give me a moment and I'm going to play this video for you.
At the time he carried out the experiment, the atom was thought to be a blob of positive charge with negative electrons embedded inside it. Now Rutherford set up an experiment to direct a beam of alpha particles, which he knew to be heavy positively charged particles, and we now know to be the nuclei of helium atoms, through a very thin gold foil. The brass can in the centre of the picture contains a small americium-241 source producing alpha particles. Most of the particles are absorbed in the brass. There is a small opening producing a beam of alpha particles. They pass through a gold foil, which is about 1.5 microns in thickness, and they are then detected by one of the two detectors set up behind the foil. One of the detectors counts particles going straight ahead, which is the majority, and we count a rate of between 1 and 2,000 per second. The second counter we can move to measure the scattering rate as a function of angle. Now, the experiment that he and his colleagues carried out was very laborious. It involved them sitting for hours in a dark room, holding a tiny fluorescent screen and looking just by eye for flashes of light on the screen. We've replicated that with modern detector technology. In its current position behind the foil, it will measure one count every few seconds. As Rutherford deduced, most of the gold atom's empty space, so the alpha particle just goes straight through, doesn't see anything, and goes through in a straight line. Occasionally, one of the particles will come close enough to the nucleus of the gold atom that it will be deflected by the electric field from the positive nucleus. If it comes at a glancing blow, it will be deflected through a small angle. If it hits it head on, it will just bounce straight back. And it's fascinating, I think, to them that this was telling us something very important that we didn't know about the very deep structure of matter. It showed that the atom had a heavy nucleus with mostly empty space with electrons distributed around it, which is exactly the picture we now have. It was also the start of particle physics. What Rutherford was doing, what we're doing here, is taking a beam of particles, firing it at a target, looking at the way the particles are scattered, and from that deducing what was going on inside the target. And 100 years ahead, we now have the Large Hadron Collider, where we do the same thing. We fire a beam of particles at a target. In that case, the target is another beam coming the other way. We look for the particles being scattered out of that collision process and try to deduce what was going on in the collision from the behaviour of the scattered particles. And all that comes from Rutherford's original idea of firing a beam at a target. So in a century, we've come from an apparatus that would fit on the desk, that was at the cutting edge of physics, to the Large Hadron Collider, which is 27 kilometres in circumference. What was happening was that the alpha particles were going through and missing the nucleus, because the nucleus is extremely small and the atom, by comparison, is very big. So it's almost all empty space. And we had to wait a long time before one of those alpha particles hit the nucleus almost head on and bounce back into our detector.
Okay, so that was a lovely video that you all saw there to explain what we've been talking about. And, whilst we're talking about atoms, let's move on to the next area. We've gone through Dalton's discovery. We've gone through Ernest Rutherford's experiments. And where does that leave us? What did Rutherford find? He found a nucleus that was positively charged. But what about the electrons? So Niels Bohr later on suggested that electrons orbited the nucleus in shells, nonetheless, as we all know now, like planets orbiting the sun. So this is again where you guys can look at the Royal Society of Chemistry resources in the pack. There's a very good activity for you to conduct in terms of going through the history of the discovery of the atom. But this diagram here is something that all chemistry teachers have become very familiar with, and something that we very often use in our teaching. So the modern atomic theory, or the modern atomic model, quite simply explains that electrons exist in a cloud around the nucleus, and that they can be thought of as waves or particles or mathematical functions, and that we know the nucleus is quite dense and heavy, and there's quite a lot of space, as Rutherford's experiment showed, where the electrons create the volume. So let's have a look now when we're going into how we use this information in the periodic table in our cycle 3 chemistry teaching. So the number of protons define an element. So when we're looking at mass and atomic number, Z is the atomic number, proton number, and A is the number of protons plus the number of neutrons. Some nice revision there for you all. So when we look at this information, helium, 2 electrons, 2 protons, 2 neutrons. The number of protons is always equal to the number of electrons. So this is where we start to look at our subatomic particles in much more detail. The 3 that we need to know in detail for cycle 3, of course, proton, neutron, and electron, their relative charges, their relative mass, and the common depiction that you will find in the textbooks and any activities that you might want to do with your students. This takes us on to then the concepts of relative atomic mass, AR. We all know, or let's remind ourselves, that elements have different isotopes. The mass stated in the periodic table is a weighted average, and that is relative to a particular standard. That standard is, of course, that a mass of 1 is equal to 1/12 of the mass of an atom of carbon-12. Good old carbon-12. So relative atomic mass is equal to the average mass of the naturally occurring isotopes of an element relative to carbon-12. Right, so let's have a little go at an activity. Isotopes. So we know the number of protons is the soul of an atom. Most elements have different isotopes, atoms of the same element with a different number of neutrons. Chlorine, as an example, has 2 naturally occurring isotopes, 35 and 37. So, what is the relative atomic mass of chlorine? Let's have a look. Can you work it out? Yeah, that's right. There we have the mass of each isotope multiplied by the percentage abundance, which gives us 35.49. So what you have now on the screen in front of you is the method to calculate relative atomic mass. What I'd like you to do now is partner up, and then I want you to choose at least 10 elements with different isotopes from the periodic table. And I want you to devise a quiz that you're going to give to each other. Once you've devised the quiz, then you will go on to give each other the quiz. So I'll display the instructions in just a moment on your screens. Okay, so now you've done this, let's have a look at the instructions for the activity I was just talking about. Choose a partner. Individually choose 10 elements, not those that are the same as your partner. Devise a quiz to test your partner on the elements and include questions on relative atomic mass, subatomic particles, and isotopes, as well as calculating AR. Give your partner the quiz and then grade each other's answers. I'm hoping that you'll all come up with a number of different quizzes that you can then share together and take back to your classrooms. So 15 minutes to do that. I would say 10 minutes to write your quizzes and 5 minutes to conduct them and grade them. We can, of course, take a little longer if you need to. I'm here in the chat box if you need to ask me any questions, and if you're doing this later, once it's been recorded, do have a go. These jigsaw activities are very good for using in the classroom and also reinforcing skills and knowledge that we need at Cycle 3. So let's dig a little deeper into electronic structure and the periodic table. What do we know about it? We've talked about today already atomic mass, the number of electrons, and the subatomic particles that we find. We've reviewed the fact that the mass and atomic number are related to the subatomic particles. The mass number is protons plus neutrons, and the number of protons is the atomic proton number. So how are these related to how everything is displayed in the periodic table? Well, let's have a look. When we look at the periodic table, we generally get elements arranged according to the number of electrons in them and which shell they fill. So you can see this reminder diagram here shows you that if you look at helium, where it would be, or hydrogen, for instance, we're only looking at the first outer shell, 1s. And as we move through, you can see a pattern developing there. So according to the number of shells filled, the periodic table displays different atoms. And then we now know that the larger the number of electrons, the more volume that atom occupies, and the denser the actual nucleus of that particular element. So let's have a look now at the electron configuration in the periodic table in a little bit more detail. You can see which number of shells going from S to P to F are being filled in different trends across. Let me see if you can remember if we're talking about periods or groups there. The different blocks of the periodic table are directly related to the number of electrons in their outermost shell. So, very famous scientist that we all know about, Mendeleev, first periodic table was published by this Russian chemist Dmitry Mendeleev, and he had some gaps. Not all of the elements that we now know exist had been discovered yet, so he left these empty spaces. They did get discovered by 1886, and what Mendeleev did was he started to arrange all the known elements in rows by increasing mass. So we now know that increasing mass is directly related to the number of protons in the nucleus. And then he started to group elements with similar properties into columns. After Mendeleev's work, we then had some further development that we'll look at today with Moseley. And in 1911, the English scientist Henry Moseley discovered that the elements fit into patterns when they are arranged according to their atomic number rather than their atomic weight. And that is when we came up with the periodic law that states that the physical and chemical properties of the elements are periodic functions of their atomic numbers. Now, what does this mean to us today? Well, if we look at the periodic table and the work that we do with it in chemistry in cycle 3, very often it's to do with, yes, the physical and chemical properties of elements, but it's also to do with understanding electronic structure and being able to teach our students about electron configuration and ourselves be able to demonstrate a good knowledge and understanding of this. So, having said that, a quick exercise for you all. Listed a few atoms there, and what I would like you to do now is just spend a few minutes looking at your periodic table and filling in the blanks. So we're looking for the number of protons, electrons, and neutrons. I shall be back with you in exactly 15 minutes. Try to do this as an individual task and see what answers you come up with, and then we'll review them in just a moment. 15 minutes for that task. Okay, let's see how we all did with our answers here. So let's start off with sodium. Did we get that right? Check your answers. What's RH? Who can remember? Did you have to look hard for RH? RH. Any shout outs? What is RH on the periodic table? Who can pronounce it correctly? Waiting for an answer. Anybody tell me what it is? Rhodium. That's correct. Don't pronounce the H. Then we've got phosphorus. Then the last of the halogens. What is the last of the halogens? Who knows what the last of the halogens is? Any shout outs? Which one is the last of the halogens? Waiting for an answer. Tennessine. Okay, Xe, we know. What's the only liquid non-metal? The only liquid non-metal. Bromine. Then we have lithium with a charge. Very good. Then we have fluorine with a negative charge. And carbon 14, not 12, carbon 14. So check your answers there, see how you did with that task, and just think about this in terms of critical thinking again and different ways to get students to interact with the periodic table. You can see that not all of the atoms were given to you with their symbols. You've had some descriptions there for some of them. It's a very nice activity to get the brain cells working. Okay. So now we've done with that activity, let's have a quick recap of electronic structure. So the first 20 elements have their electrons arranged in a very simple manner. The first energy level can take up to 2 electrons, the second energy level can take up to 8 electrons, and the third energy level can take up to 8 electrons. Basic chemistry that we're all familiar with. And then let's have a look at this electron structure in a little bit more detail. So as an example, all the group 1 elements have 1 electron in the outermost energy level. Look at the electron configuration for lithium and look at it for cesium. The last shell always has 1 electron. So that's a very good rule to remember. The orbitals fill with the electrons from the lowest energy level first, and then they move through the number of electrons per shell, which is 2, then 8, and then 2. So group 1 always have 1 electron unless it is an ionized atom in the outer shell. Okay, let's have a look. Can we apply that? So just take a few minutes, see if you can fill in these orbitals. Keep in mind the rules that we just went through. Okay, great. Let's have a look and check if you got those answers right. I'm sure you did. And this is something that we quite often do with our students. Again, there's Royal Society of Chemistry activity sheets that we can use when we get to our dot and cross diagrams, which incidentally students often find a lot easier to use in depicting how orbitals fill, or as we know it, electron configuration. So now that we've had a go at filling the orbitals, let's try and recap our understanding of the atomic orbitals. So you saw previously what we call, the Lewis dot and cross diagram. And when we think about the shells that we find our electrons in, we need to think of them as energy levels, which consist of orbitals. So the Lewis dot and cross diagrams, such as the ones you saw earlier on in the slides, there's an example for cesium. We can see the electron configuration is 2, 8, 8, 1, and we see simple dots depicting each electron in each of the energy levels or the shell. Now, each of these are right now represented to you just as circling the nucleus in rings. However, in reality, electrons move along paths that are much more complicated than these rings that you see here. And those paths are known as atomic orbitals or subshells. So there's several different orbital shapes, and can you remember what we refer to them as? We refer to them as the S, P, D, and F. So you've got to think of your orbital as a 3D entity. So there's the S orbital, and we've got the P orbitals. And that's what we'll focus on right now. So each orbital can hold a maximum of 2 electrons. Each orbital can hold a maximum of 2 electrons. And each main level can hold a maximum of 2. Each main level is subdivided into sublevels based on the orbital type, e.g. the P or the S. And if we look at the energy levels, the first energy level only contains the S orbital. The second energy level contains 1 S orbital and 3 p orbitals, and so on and so on. So let's have a look at that in a little bit more detail, shall we? So the electron structure, let's have a look at it. You can see in the first energy level we have 1s, where we can put 2 electrons. Then in the second energy level, we have 2s and 3p energy levels. 2p energy levels, sorry, where we can put 2s and 6p electrons. And then we go up to the third main energy level, 3s and 3p, and then 4s. So the s orbital is at a lower energy than the p orbitals. And such orbital diagrams help us to determine and help students determine the electron configuration of an element. After all, an element's electron configuration is the arrangement of the electrons in the shells. So the main points to remember, as per the previous slide, are each orbital, s or p, can only hold 2 electrons. Electrons that occur together in an orbital are called an electron pair, and an electron will always try to enter the orbital of the lowest energy. An electron can occupy an orbital on its own, but it would rather occupy a lower energy orbital with another electron before occupying a higher energy orbital. In other words, within one energy level, electrons will fill an s before they fill a p. S subshells can hold 2 electrons, p subshells can hold 6 electrons. So electron configuration is used to rationalize chemical properties, because we've seen that on the periodic table the elements are grouped according to their chemical nature, and they in turn are grouped to their outermost electron. So linking electronic structure to the periodic table is a very good way to help students understand electron structure and the chemical properties of different elements. So in our learning objectives, we said we're going to learn about the Aufbau principle. Let's have a look at that next. Okay, so let's take a look at the Aufbau principle then. Something that many of you will know how to do and how to teach to the students, but what does it actually tell us? The Aufbau principle determines the number of electrons that the atom has. And you can see a diagram there for fluorine. I have to admit, when I was a student doing my A-level chemistry back in the UK, my chemistry teacher never named this process for me. Often naming things for students and relating them to history and how things were developed helps create better understanding. So number 1, you determine the number of electrons that the atom has. We know we do that by looking at the periodic table. We then fill the s orbital in the first energy level. We've established that rule already with the first 2 electrons, lowest energy levels first. We then go and have to the next energy level where we also fill the 2s first with the second 2 electrons. Then we put 1 electron in each of the 3p orbitals in the second energy level. It's very often a mistake that students make, and you will see here in the 2p, students will often fill this first, but remember that we put 1 into each of the p orbitals first, and then we go back and place a second electron in each of the 2p orbitals. Very important rule of the Aufbau principle. And you continue in that manner through each of the successive energy levels. And again, When you go through your pack, you will find some Royal Society of Chemistry worksheets that you can both try and use for your students. I would recommend you all now take just 5 minutes and test each other on using the Aufbau principle. Identify some elements from the periodic table and see if you are able to draw the electron configuration using the Aufbau principle for at least 5 different elements, and share with each other, check each other's answers, and then we'll come back and have a look at them. Okay, so that was a very good activity, and we looked at using the Aufbau principle, nice and simple way of depicting the electron configuration of an atom. Now what we'll add into that is Hund's rule, if you may. So Hund's rule defines the behavior of unpaired valence electrons. Okay, so unpaired valence shell electrons, very important, because that, as we all know, an unpaired electron provides insight into the atom's reactivity and stability. So according to the Aufbau's rule, we'll always fill up an empty orbital before they pair up. That's Aufbau's principle. Remember when we looked at the p orbitals, there's one electron going into each orbital first. Now, electrons are negatively charged, so as a result, they repel each other. So they do tend to minimize repulsion by occupying their own orbital. That explains why we fill up one at a time in each of the p orbitals. Now, with Hund's rule, unpaired electrons in singly occupied orbitals, as you can see in the diagram there, have the same spin. So if all electrons are orbiting in the same direction, they meet less often than if some of them orbit in opposite directions. So in that case, repulsive forces increase, which separates the electrons. Therefore, the spins that are aligned have a lower energy. Technically, we can easily describe it as electrons in a sublevel could either spin up or spin down. And once the first electron in a sublevel is chosen, the spins of all the other electrons in that sublevel depend on that first choice. So as you can see now in the diagram, we have arrows showing the spin up or down. So when we want to apply Hund's rule, what we do is we take the electron configuration. Let's say we've got oxygen in front of us here. Okay, so oxygen has 8 electrons, and we can write the electron configuration just as you see it there, 1s2, 2s2, 2p4. The orbital is drawn as follows. The first 2 electrons pair up in the 2s, correct. That leaves 4 electrons which must be placed in the 2p orbitals. Can you see what the difference is in those diagrams? Because remember, Hund's law is all about electron spin and repulsion. According to Hund's rule, all orbitals will be singly occupied before any is doubly occupied. And this is something that students often get wrong. So you can see where we've got the green correct diagram. Yeah. We've got electrons occupying all of the 2p orbitals, and the last two are single electrons and they have the same spin. And that's very important for students when they are applying Aufbau's principle and applying Hund's rule to ensure that they understand how to predict the electron configuration of an atom. Why do we need to know about the electron configuration of an atom in chemistry? We need to know about it because it allows us to predict stability, make predictions about reactions with formulation of chemical compounds or molecules. And it helps us to understand the behavior of all chemicals. That's a very good way to put it to students, that the electron configuration of an atom allows us to understand or predict the chemical behavior of an atom. From the most basic, like hydrogen and helium, to the most complex biological proteins and molecules that we find in the human body. So that was the Aufbau principle and Hund's rule. And if you're still with us, what you will find is a very nice exercise in the Royal Society of Chemistry handouts in the pack that come with this training. And it's just a quick activity at the end where what we've done is provided you with some basic elements that we come across in our chemistry teaching. And just to wrap up the activities for today, what we'd like you to do is to be able to actually draw the electron configuration for each element and then use Aufbau's principle and Hund's rule to be able to depict the electron configuration in a diagram. So have a go at that for 20 minutes and let's see how you do. Okay, welcome back. Some very good answers there. We'll have a look. There are the solutions for each of the elements that were given to you, and make sure that you're applying Aufbau's principle and Aufbau's rule when you are looking at Hund's rule, Aufbau's principle and Hund's rule when you are drawing the diagrams for these. Very good rules to apply when we're looking at electron configuration. So that's us wrapping up now for the day. And if we have a look, we did some great work on the scientific method, scientific notation and derived units. Properties of matter, don't forget to have a look at that very in detail pack in the resource guide. The electronic structure, and then applying the Aufbau principle as well as Hund's rule. I hope you've enjoyed the session today, and I hope you'll be back with CEC at some time in the near future and we can do some more chemistry. There will be a day 2 of Foundations of Chemistry, and I look forward to seeing you all then. Those of you that are with me now, you can drop me some messages in the chat box if there's anything you'd like to ask. And those of you that are watching the recording, I hope it was useful and I hope it identified some areas of revision in your chemistry foundation knowledge. Thank you from CEC.